Hi folks, I hope you are doing well. Recently I discussed with you the switching power supplies that were the non-isolated. I mean input and output ground was common and there was no separation of input power from output power. But these topologies of switching power supplies can be used for low voltages input and outputs. But we know that we normally have to sometime operate the power supply from the mains input, which is supplied in the households, like 220 volt AC or 230 volt AC. So if we don't separate the input side from the output side, or in other words don't isolate, then the hazardous situation can occur and it can create electrical shocks. So today I will discuss with you the switching power supplies that are isolated versions. I mean input ground is separated from the output ground and there is isolation barrier in between them in the form of a transformer. First such a power supply that I will discuss with you today is the flyback topology or flyback converter. Before going into detail of the flyback converter, I want to discuss with you the transformer used in it. Normally when we use the 50 hertz transformer, old type transformers that were available 1 or 2 decades ago, or in them when the input power was supplied to the primary side of the transformer, at the same time we can get the output power or output energy, or in other words at the same time it is supplied to the output. But in the flyback converter the story is different. I mean when the input or primary winding is conducting, the output or secondary winding is not conducting, and similarly when primary winding is off, then the secondary winding is conducting. So in order to this happen, the energy is stored in the magnetic core, so that when primary winding is conducting, the core is charged, and when primary winding is not conducting and the output side secondary winding has to conduct, this stored energy of the in the transformer core is supplied in the form of the output voltage. But there is another difference, that in the forward type of converters we don't need to have the create a gap in the ferrite core, as the flux buildup is less. Only magnetizing current is flowing through the transformer normally, and all the energy at the input is instantly converted to the output, and no additional flux is generated in the core. But in the flyback converter, I told you that the energy is stored in the transformer core when the primary winding is conducting. So if the we want to supply to some load, output load, some power, then this stored energy should be sufficient in magnitude. But we know that if you charge the primary side winding, then the flux in the core gets increased, and sometimes this flux increase is such a of high magnitude that the core saturates, and when it saturates, then there is no flux. The path remains in the core, and the flux now start flowing through the output outside of the core, and it acts like a air core inductor. And we know in air core inductor its resistance is very small, and so thus the transformer core gets saturated, and the high amount of current start passing through the primary winding, which can destroy the primary MOSFETs or other circuitry and can blow the fuse. To overcome this problem, we normally create a gap in the middle section of the leg, manually or machined, because as I told you that normally the air core inductor, the flux amount is very less, but in the ferrite core we can pass in a large amount of flux. But if we force this large amount of flux through the air gap also, which we normally do in the flyback converter, because the gap is in between the two sides of the central leg, so these same flux that is flowing through the core also have to be flown through the air gap. So this tremendous amount of flux in the air gap creates a very huge amount of air core inductor in the air gap, so the energy is stored in it. A large amount of energy can be stored in it without the core going to saturation. And when the primary MOSFET is turned off, this huge amount of energy can be supplied to the output. Due to some limitations, we normally use the flyback converter from let's say 5 watt to up to 150 watts. And some example of the flyback converters in daily life are that of the mobile phone chargers. And normally mobile phone chargers and small form factors of the adapters like laptop adapters are normally designed in the flyback converter configuration. The flyback converter has the same similarity as the buck boost converter that we discussed in the non-isolated version of power splice, because in the buck boost converter, when the switch is conducting, the energy is stored in the inductor and no energy is supplied to the output. And when the transfer of this energy is supplied to the output and no energy is coming from the input side, so only charged inductor energy is transferred to the output. Similarly, in flyback converter, the only charged amount of energy in the primary winding is transferred to the secondary winding. The flyback converter can be operated in the two modes. One is a discontinuous conduction mode and other is a continuous conduction mode. In discontinuous conduction mode, the energy, all the energy that is stored in the ferrite transformer when a primary winding is being charged is completely supplied to the output secondary side where the load is connected. And so then next cycle start from the fresh. And but in the continuous conduction mode, the charge time is increased, I mean more than 50% duty ratio. So when the primary winding is not conducting, the some energy supplies to the output and the remaining energy remains in the transformer core, and it adds up with the next switching cycle, and then remains at a fixed value when a steady state condition is achieved. But there is a disadvantage in the continuous conduction mode that I discussed with you in the boost converter and the buck boost converter, that when the primary winding is charged with more than 50% duty ratio, in scenarios when the load is increased or heavy load is applied to the output side, the inductor charge time is increased more than 50% duty ratio. But because we know that in the buck boost and boost converter and the flyback converter, the output side energy, the energy on the output side is supplied only when the transistor turns off and secondary winding starts conducting. So but we know that we have charged the primary winding with more than 50% duty ratio, so the small amount of time gets remained when this energy has to be converted to the output load side as output voltage. So it create a reverse effect. I mean, we want to splice the more power to the output according to the more current demand, but the output energy transfer phase has been time has been reduced. So this is also called the right of plane zero. That is why we normally avoid operating the flyback converter in the continuous conduction mode. Uh, but there are also some disadvantages of the discrete conduction mode as well. I mean, the primary and secondary side currents spikes are much of higher magnitudes, and but there is an advantage that because the in one switching cycle the other energy is supplied to the output, so diode reverse recovery effect has got eliminated, and it doesn't produce spikes which can generate the EMI. So this was today's discussion about the flyback converter. Flyback converter, as I told you, that it is different from the forward type of converter that we will discuss later on. In forward converter we need output LC filter as well, so that the ripple has been reduced to minimum and pure DC is source has been provided at the output. But this LC filter adds to the components count and also the cost of the power supply. In the flyback converter we don't need the LC filter, we only capacitor is enough, and the L section can be compared in the form of the secondary winding, which is also used as the L section of the LC filter. I mean, the transformer secondary winding acts as a inductor for filtering the output, so we don't need the extra LC filter. Flyback converter, another advantage of using flyback converter is that we can supply it from the mains universal input. I mean, whether it is 110 volt or 220 volt AC, and we don't need a make break switch to set it to 110 volt value or the 220 volt value, as you may have seen in the old version of the ATX power supplies, I mean computer power supplies, tower casing type of power supplies, where there is a switch of 110 volt AC or 220 volt AC. In flyback converter we don't need a switch, and it can supply directly from the mains, either it is whether it is 110 volt AC or 220 volt AC. As long as input capacitor selection is concerned, we normally select the input capacitor as 3 microfarad per watt rating. I mean, suppose that the flyback converter maximum input power that flyback converter utilizing is 100 watt, then according to the 3 microfarad per watt rule, we will need 100 into 3, I mean 300 microfarad capacitor. So the nearest standard value is 330 microfarad, so we will need a 330 microfarad input capacitor for the 100 watt maximum input power of the flyback converter. This was our today's discussion about the flyback converter, and Flyback converter is a very versatile converter, and it can be used when we need the multiple output windings or multiple output voltages with good line and load regulation. And also when we want to use it where the input can be universal, I mean either 110 or 220 volt. And also in Flyback converter, I told you that the component count is minimum because no LC filter is required. So guys, I hope you have grasped some knowledge about the Flyback converter today. So stay connected, and thank you very much.